Hello friends, welcome to engineering tutorial. In my video related to generation of double sideband suppressed carrier signal, I discussed about two methods of how we can generate a double sideband suppressed carrier signal. One was the balance modulator method and the other was the ring modulator or the double balance modulator. Now in one of my videos related to amplitude modulation, I discussed about the balance modulator method of generation of dsb-sc signal. So you please check out that video before you watch this video so that you can understand it in a better way. So in today's video we will be discussing about the ring modulator method or the double balance modulator method for generation of a double sideband suppressed carrier signal, in which only the lower and the upper sidebands are passed or transmitted and the carrier signal component is suppressed. So let's get started. So this is the circuit diagram for a ring modulator or a double balance modulator. Okay, as you can see two transformers, 4 diodes and a band pass filter. The message signal is connected to the primary winding of the first transformer, while there are 4 diodes which are connected in this fashion. The output, which is fed to the band pass filter, is taken across the secondary winding of the last transformer or the second transformer. A square wave carrier is applied through center tapped connection to the secondary winding of the first transformer and the primary winding of the second transformer. Here it is written as EC cos omega CT, the square wave carrier, but it's actually in the form of a bipolar square wave carrier, okay, which is given in terms of Fourier series expansion. Here, as I couldn't have written the whole expression, so I just written it like this, but it's actually a bipolar square wave carrier in terms of cos omega CT, which is written as the Fourier series expansion. So please you can have a screenshot of this part, or you can draw this diagram in rough, so that when I discuss about the mathematical description of how the dsb-sc signal is generated, it will be easier for you to understand this. So please pause the video, draw this diagram in rough, or have a screenshot of it. Okay. So basically this is a switching modulator. Okay, it is also called as a switching modulator, the double balance modulator. So you get the output signal in this form, K into MT into cos omega CT, which is the standard expression of a double sideband suppressed carrier signal. So let us go into the mathematical explanation and the working principle of it. Now, please refer to the screenshot or the rough diagram that you have drawn in your rough copy while you see these things. Okay, so during the positive half cycle of the bipolar square wave carrier, the diodes D1 and D3 conduct. It is because the positive end gets connected to the P of the diodes D1 and D3, while and the negative end is connected to the N. As a result of that, the diodes D1 and D3, they get forward biased and behave as short circuit, while the other diodes, two diodes D2 and D4, they are reverse biased and gets open circuited. As a result of that, terminal A gets connected to C and terminal B gets connected to D. Okay, refer to the rough diagram that you have drawn or the screenshot that you have taken of the circuit diagram. Next, during the negative half cycle of the square wave carrier, diodes D2 and D4 conduct because they are forward biased. Because the N ends of D4 and D2, they are connected to the negative polarity of the square wave carrier, while the P ends are connected to the positive polarity. So they behave as forward bias diodes and act as short circuit, while the other diodes D1 and D3 are reverse biased and open circuited. As a result of that, A is connected to the point A gets connected to B and the point B gets connected to C. Now, we always get the output in terms of the message signal. Now, as I said, the carrier signal which is used is actually a bipolar square wave pulse train, which is a series of cosine signal waves and is given or expressed in terms of Fourier series expansion. It is expressed as this: omega 0 t, which is the bipolar square wave pulse train, which is given by 4 by pi cos omega ct minus 1 by 3 cos 3 omega ct plus 1 by 5 cos 5 omega ct, and so on. This is the bipolar square wave carrier, the carrier signal which is applied as center tapped connection to the transformers. Okay, please keep referring to the rough diagram or the screenshot that you have taken of the circuit diagram. Okay, so this is the square wave carrier which I was talking about, given in terms of Fourier series expansion. Okay, which is looks something like this, while the message signal or modulating signal, which is in cosine form, looks like this. Okay, now the output is given by or is expressed as the product of the modulating signal and the bipolar square wave carrier, which is given by 4 by pi into mt cos omega ct minus 1 by 3 mt cos 3 omega ct plus 1 by 5 mt cos 5 omega ct, and so on. Now, we need only this part, mt cos omega ct. We do not need these parts, because here the frequency components which are present are multiples of the carrier frequency, which are very high, and we do not require them. The double sideband suppressed carrier signal is only this part, mt cos omega ct. So for that purpose, we will use a band pass filter having a pass band frequency range defined from minus omega c to plus omega c. As a result of that, these frequency terms or these frequency components will get suppressed, and only this part will be passed. So the output of the band pass filter is given by 4 by pi mt cos omega ct, which is equal to kmt cos omega ct. This is the required dsb-sc signal. So you see here, it can be written as k em cos omega mt cos omega ct, where k is 4 by pi. Okay, 4 by pi is written as k. Now it can be written by applying the trigonometric identity we have applied here: 2 cos omega ct into cos omega mt, which is equal to k by 2 into em cos omega c minus omega mt plus cos omega c plus omega mt. This is the lower sideband and this is the upper sideband. Now this is the required double sideband suppressed carrier signal. Okay, so this is the double balanced modulator method for generation of a double sideband suppressed carrier signal. Here we have used 4 diodes. That's why, so there are even number of diodes. Okay, even number of diodes we have used. That's why it's called as a double balance modulator. Okay, we have used even number of diodes, 4 diodes, so that's a double balance modulator. The output is given in terms of the product of the modulating signal and the bipolar square wave pulse train carrier. Okay, the important thing to take note of is the bipolar square wave pulse train signal, okay, which is given in terms of the Fourier series expansion. So that is the important thing to remember in this case, as well as the expression, the output expression, which is the product of the modulating signal and the bipolar square wave pulse train. Then the high frequency components are suppressed with the help of a band pass filter having a pass band frequency range from minus omega subscript c to plus omega subscript c, so that only this part is passed while the other high frequency components are suppressed. So finally we get the required double sideband suppressed carrier signal. Okay, so here we have discussed about the double balance modulator method for generation of double sideband suppressed carrier signal. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, communication and instrumentation engineering. Have a great day. Thank you very much.